A satellite 430 miles above Texas picks up something no engineer standing on the ground can see. A 2.5-mile-long structure is moving, and the two halves are moving in opposite directions. Below it, a river feeds drinking water to more than 3 million people. The dam has zero backup infrastructure. If it fails, Houston has nowhere else to turn. What happens when the only thing standing between a major American city and a water crisis starts pulling itself apart from the inside? Livingston Dam sits on the Trinity River about 70 miles north of Houston in Polk County, Texas. It stretches 2.5 miles across the river valley, rises 90 feet above the original streambed, and is built almost entirely out of compacted earth with a concrete spillway section in the middle. It is the largest single-purpose water supply reservoir in the entire state of Texas, and that single purpose is keeping Houston's taps running. The Trinity River Authority built and operates the dam under contract with the city of Houston, which owns 2/3 of the water rights to the reservoir. The remaining third stays under the authority's control. Houston's east and southeast water purification plants draw raw water from the Trinity River at a pump station 35 miles downstream of the dam. Those two plants alone serve more than 3 million customers across the greater Houston metro area. Every day, roughly 806 million gallons flow from that river into the city's drinking water system, accounting for about 70% of Houston's total daily supply. One detail about this dam matters more than any other for the rest of this story. Lake Livingston was built with zero flood control capacity. Flow through the dam is controlled by 12 tainter gates in the concrete spillway, and their operation mirrors the river. When the Trinity rises, discharge increases. When it falls, discharge drops. It stores water for supply, but it was never designed to absorb a surge. In the early 1960s, Houston was growing fast and running out of water options. The Trinity River was the only source capable of scaling with the city's projected demand, and the federal government was not writing the check. The Trinity River Authority and the City of Houston financed the entire project through revenue bonds. No federal money went into construction. Brown and Root designed it, Forest and Cotton Incorporated built it. Construction began on May 28, 1966, and finished on August 29, 1969. Deliberate impoundment of water started in October 1968, before the dam was even completed. The engineering choice was earthfill, meaning the dam is built from layers of compacted soil and rock rather than poured concrete. In the 1960s, this was standard for large reservoir dams. Earthfill was cheaper, scaled well with local materials, and suited the geography of a wide, flat river valley. But the trade-off was known from the start. Earthfill dams are more vulnerable to internal erosion and differential settlement over time. A concrete dam cracks visibly. An earthfill dam erodes from the inside, and the surface can look fine while it happens. The scale of what they moved to build this thing is hard to overstate. Workers cleared 40,000 acres of land. The project required acquiring 700 parcels of property and relocating 200 families. 2 cemeteries had to be moved, 196 graves were exhumed and reinterred somewhere else. The total cost came to roughly $84 million in 1969 dollars, over $700 million adjusted for inflation. The construction contract alone was $16 million. Highway 190 had to be rerouted for $7 million. 5 farm-to-market roads, utility relocations, and the land clearing added millions more. Every dollar came from bond revenue, redeemed through water sales as Houston kept growing. The first real sign that this dam was more fragile than it looked came in September 2005, when Hurricane Rita swept through East Texas. Rita's counterclockwise winds blew north to south down the full length of the lake, generating waves up to 4 feet high that hammered the dam's upstream face for hours. When the storm passed, 11,000 feet of riprap, the layer of heavy protective stone covering the earthen embankment, had been stripped clean. The bare soil underneath was now exposed directly to the water. The Trinity River Authority dropped the pool level by 4 feet as an emergency measure. FEMA covered 75% of the $9.6 million repair bill, with the City of Houston paying the rest. Contractors hauled in over 72,000 tons of limestone and nearly 16,000 tons of bedding rock across thousands of truckloads. Repairs wrapped up by late April 2006. Rita was the first warning. The dam's surface protection had failed, and surface repairs alone do not address what might be happening deeper inside the structure. The European Space Agency operates a pair of satellites called Sentinel-1, orbiting about 430 miles above the Earth. They carry a radar system that bounces radio waves off the ground and measures how long the signal takes to return. The technique is called Interferometric Synthetic Aperture Radar, or INSAR, and it can detect vertical movement down to the millimeter. Think of it like a ruler held from space, measuring whether the ground has shifted since the last pass. A team at Virginia Tech, led by geophysicist Mohammad Karami and senior researcher Menashir Shizeh, used 10 years of Sentinel-1 data, spanning from 2015 to 2025, to study 41 high-hazard dams across 13 states and Puerto Rico. Every single one of the 41 dams showed some degree of vertical movement. Most of it was minor. Livingston Dam was different. It recorded the highest sinking rate in the entire study, the northern portion dropping 8 millimeters per year, while the southern portion rose by the same amount. Two halves of the same 2.5-mile structure moving in opposite directions simultaneously. This is called differential settlement. Different sections of the foundation are shifting at different rates, and the structure above has to absorb that stress. In an earth-filled dam, this creates internal tension that never shows up on the surface. It can open invisible pathways through the compacted core, a process engineers call piping. Piping is how earth-filled dams fail. Water finds a channel through the interior, erodes it wider, and the process accelerates until the structure gives way. It can happen fast, with very little external warning. The Army Corps of Engineers' National Inventory of Dams already classified Livingston in unsatisfactory condition, the lowest rating in the system. Karami presented these findings in December 2025 at the annual meeting of the American Geophysical Union. The Virginia Tech team was clear. These are preliminary findings, not proof of imminent failure. Satellite data tells you where to look. Physical inspection determines what is actually happening inside the dam. Karami compared it to an anomaly on a medical scan. It tells you to investigate. It does not mean the patient is dying. The Trinity River Authority did not respond to the Washington Post's request for comments before the story was published in January 2026. 6 months before the Virginia Tech team went public, the dam had already spoken for itself. In the spring of 2024, heavy rainfall pushed the Trinity River to record levels. On May 4, the spillway's discharge hit 124,260 cubic feet per second, shattering the previous record set during Hurricane Harvey in 2017. On May 16, the day a deadly derecho tore through southeast Texas, the Trinity River Authority activated its Emergency Action Plan. The designation was Non-Failure Abnormal Condition. Inspectors had found a partial failure of the left downstream training wall and erosion eating into the area around it. Then came June 26. After several failed attempts to inspect the spillway up close, crews finally closed all the gates long enough to get a look at the stilling basin, the structure directly below the spillway designed to absorb the force of water being released. What they found was severe. The force of the water had stripped all of the riprap and scoured through the clay fill down to the apron of the dam. Engineers wrote in their federal filing that the damage threatens the integrity of the dam and declared it an emergency condition that requires immediate action. 2 days later, on June 28th, the Trinity River Authority declared a potential failure watch, the formal designation one step below active failure. Crews worked around the clock. They poured nearly 1,000 cubic yards of concrete into the stilling basin to stabilize it. Repairs were completed and tested by July 7, 1 day before Hurricane Beryl made landfall in southeast Texas. But the emergency repairs addressed what the water had done to the surface. They did not address why independent satellite data was showing the structure itself was in motion. Before the Virginia Tech study was ever published, a London-based satellite monitoring company called Value Space had already been watching Livingston Dam. Their analyst, Ray Pold, conducted a 3-year assessment and identified 5 distinct areas of movement on the dam's slope and spillway. A 350-foot section on the west side of the spillway showed what Pohl called significant deformation. He found similar movement on the east side. Those areas were sinking at a rate of 0.22 to 0.55 inches per year, and the rate was accelerating. The critical number? Movement on the spillway had accelerated 3-fold between September 2023 and mid-2024. 2 independent satellite analyses, conducted by 2 separate teams using different datasets, reached the same conclusion. Something is happening inside this dam that surface repairs alone cannot fix. In November 2025, Congressman Pete Sessions announced that FEMA had approved a $30 million grant to reimburse the Trinity River Authority for its 2024 emergency repairs. That money covers what was done. It does not fund what comes next. Livingston Dam is one data point in a much larger problem. The same Virginia Tech study flagged Roanoke Rapids Dam in North Carolina, sinking at about 7 millimeters per year. Dominion Energy, which operates that dam, retained Gannett Fleming engineers to investigate. They found the cause: alkali silica reaction, a chemical process that deteriorates concrete from within. Dominion responded with post-tensioned anchoring and crack grouting. The work was completed, and ongoing monitoring confirms the dam is holding. That is what acting on satellite data looks like. Across the country, there are over 92,000 dams in the United States. Nearly 17,000 are classified as high hazard potential. As of 2025, about 2,522 of those are rated in poor or unsatisfactory condition. In March 2025, the Association of State Dam Safety Officials estimated the cost to rehabilitate all non-federal dams at $165.2 billion. Federal funding has covered a fraction of that. The Virginia Tech team's goal is a publicly accessible interactive map showing real-time movement data for every high-hazard dam in the country, updated continuously from satellite feeds. Back in Texas, the water math is blunt. Houston's drinking water flows from a river controlled by a structure showing signs of internal stress. If that supply were compromised during peak demand, the consequences go far beyond low water pressure. Hospitals would ration supply, petrochemical plants would shut down intake, rolling water restrictions would sweep across one of the most economically significant metro areas in the country. The satellites are watching. 2 separate teams have confirmed the dam is moving in ways invisible from the ground. Emergency surface repairs have been made and reimbursed, but the underlying movement has not been publicly addressed. The data is telling us something about Livingston Dam. The question is whether anyone acts on it before the next storm season pushes the Trinity to record levels again. What do you think needs to happen here? Should satellite monitoring be required for every high-hazard dam in the country? Or is it an overreaction? Drop your thoughts in the comments. Subscribe for more Mega Build stories.